Hello and welcome to another video of the course. In this video, we will continue analytic design of the motor by calculation of the direct dependent variables. Okay, our design objective is here. We have these properties for our objective, the design objective of the course. The output power of the motor is 0.75. The rated motor speed is 1500 RPM. DC link voltage is 500 volts, and I set desired efficiency equal to 90%. Because I am going to use strong magnets for my BLDC motor, my design here, and I am going to check if I can satisfy this efficiency or not. Actually, I wrote here desired efficiency, not efficiency, because we didn't design any motor yet, right? We are at the start of the design. And for calculation of the value of parameters like stator current, we need to know the motor efficiency. So we assume a number for efficiency at the beginning of design, and then we do the design to see if we can satisfy this desired efficiency or not. So this is desired efficiency. And the rounding flag can be true or false. I will give you explanation of this variable later, but for now set it as true. So, okay. The output torque is equal output power divided by rated mechanical speed. This is omega m, angular speed, and it is equal 2 pi times RPS. This is revolutions per second. And as you know, revolutions per second is equal RPM divided by 60. So I implemented this equation here. The rated speed in RPS is RPM divided by 60, and omega m is equal 2 times pi times RPS, and the output torque is 4.77. Okay, this is desired output torque, and I mention again, we didn't design any motor yet, and just we are talking about our desired variables. Okay, so our motor, our design should be able to deliver this torque to the load at the rated speed, rated voltage, and the rated power. Okay, rated operating points. The motor should be able to deliver this torque. We design the motor, and then we do finite element calculations to check if the motor can deliver this torque or not. Okay, so this is one of our objectives. Okay, now let's calculate the input power and the terminal current. The input power is equal output power divided by desired efficiency. Okay, I considered the desired efficiency equal to 90%. So the input power is equal output power divided by 0.9 and is equal 0.83. The unit is kilowatt. As you can see here in this Excel file, for each design variable, we have 4 cells. The name of parameter, its value, its unit, and its description. So the input power is equal output power divided by desired efficiency, And when we calculate the input power of the motor, we can calculate the terminal current. Okay, the motor terminal current. Motor terminal current is equal input power divided by input DC voltage. So this is average terminal current. Okay, average terminal current. In ideal case, as you know, these are the back EMFs of each phase and phase currents in ideal case. Okay, if we have ideal trapezoidal back EMFs and rectangular currents, we can generate a constant torque. But as you know, our back EMFs are not like this. Actually, this is the back EMF waveform of this motor, and our current, because of commutation, we cannot have these rectangular currents, so we have ripple in both torque and input current. So because of this, I wrote here, this is the average value of terminal current. Okay, the average value of terminal current is input power divided by input DC voltage. And input DC voltage is a fixed independent variable. We calculated the input power, so I can calculate the average terminal current. I implemented this equation here. For this case, if I consider 90% efficiency, the terminal current is 1.7. So, what is the value of peak phase current, peak value of the phase current, and RMS value of phase current, and also these values for the coil, peak value of the coil current and RMS value of the coil current. As you can see here, at any instance of time, two phases are conducting. For example, in this interval, phase A is equal IT terminal current, and phase B is equal negative of IT, and phase C, the current of phase C is 0. So these two coils, phase A and phase B, for example, in this case, are in series, and the current is equal terminal current. So the peak value of terminal current is equal the peak value of phase current. Okay, we have this equation here. Peak value of phase current is equal peak value of terminal current. Actually, in the case of ideal BLDC motor, terminal current is equal its average. Okay, its waveform. We don't have any ripple in this current, a DC current. Okay, but if we consider the ripple in the current of the supply, so this is the average value. I didn't consider filter capacitor or any power electronic methods that we remove the ripple in the supply current. Okay, just I considered an ideal voltage source here, inverter, and motor. These are three phases of the motor. Okay, so this is terminal current IT. But as you know, the real currents are not like this. The real currents are, this is ideal phase current, but the real currents in BLDC motor are like this. We have a rise time, we have commutation, again we have rise, and we have a falling time. Okay, so in this case we have ripple in current, and instead of peak value we can we can define equivalent peak value. Okay, equivalent peak value to use in our analytic equations. Equivalent peak value, not peak value. Anyway, what is the RMS value of the phase current? RMS value of the phase current is equal SQRT of 2 divided by 3 times peak value of phase current. Right, because in each electrical period, actually at 2/3 of each electrical period, every phase is conducting. So this is the RMS value of phase current. I implemented this equation here. RMS value of phase current is 1.36 in this case. And what about the coil current peak value and RMS value of coil current? Depends on number of parallel paths. As you know, depending on the value of line current, we use a number of parallel paths in winding to reduce the diameter of the wire, okay, or to reduce the skin effect. So we distribute the current into a number of parallel paths. NP, you can see the value of NP here, this variable in a winding variable NP, number of parallel paths in winding. In this example, because the phase voltage is high, the line current is low. And when the line current is low, the diameter of the wire will be calculated a low number, a logical wire gauge that we will talk about it. So we don't need to use a parallel path. So I set NP equal 1 here. What are possible values for number of parallel paths? Okay, let me explain it here. BLDC motor is a double layer. The winding of BLDC motor is a double layer winding. And as you know, in a double layer winding, number of coils, total coils, number of coils is equal number of stator slots, NS. Okay, and number of coils in each phase is equal NS divided by 3, because this is a 3-phase motor. So we can do different connections. In this case, for example, this one, consider NS equal to 12 and M equal 3. M is number of phases and S is number of stator slots. So in each phase, we have 4 coils. Okay, we can connect all coils in series. So number of turns in each phase, NT phase. Actually, this is number of effective turns in each phase is equal 4 times NTC. In this case, NTC is equal number of turns in each coil. Okay, so number of effective turns is number of turns between these two terminals, two coil terminals. Number of parallel paths can be 1, 2, and 4. Okay, if we use 2 parallel paths, so we have these connections, and the number of effective turns per phase is equal 2 times NTC. And if we use 4 parallel paths, number of effective turns per phase is equal NTC. So as you can see here, in general, we can write this equation. Number of effective turns per phase, I mean number of turns between 2 terminals of each phase, is equal NTC times ns divided by m, that is number of coils in each phase, divided by np. And in BLDC motor, we should consider that when we are going to use a parallel path, the induced back EMF of each branch should be the same. Okay? Otherwise, we have circulating current, and we cannot use a parallel path. So we should check this before increasing number of parallel paths. Anyway, coil current is equal phase current divided by NP. So I implemented this equation here. I calculated a peak value of the coil current and RMS value of the coil current. Because NP is 1, these numbers are the same. Okay, we calculated till now, just we calculated these direct dependent variables. If the motor efficiency is 90%, so according to these desired values, the terminal current should be equal this number, phase current and coil current should be equal these numbers. Now, we are going to talk about output equation, motor output equation. As you know, in every electric motor, we use output equation to calculate the main dimensions of the motor, stator bore diameter and stack length. So the first step in derivation of the output equation is calculation of the motorbike EMF. Okay, if you see this simple example here, we have one coil. Actually, in this example, we neglect the saturation of the iron, so linear operation for the motor and linear magnetic properties. This is a four-pole rotor, a south pole, north, south, and north. And we have one coil here. Actually, this coil is the span of this coil is equal 180 electrical degrees integral span, right? So when the rotor is in this position, total pole flux is linked to this coil, right? So the flux linkage is equal negative of N phi G here. That is gap flux or pole flux under one pole. N is number of turns in this coil. You can see the direction of the current in this coil or direction of the winding. The magnetic axis of the coil is in opposite direction of the flux, right? This is south pole. So this is why the flux linkage is equal negative of N times phi G. These figures are from this reference, brushless permanent magnet motor design. They are Hanselman. These 4 textbooks are references of this course, and these pictures are from this reference. You can refer to this reference for detailed explanation. Anyway, if we rotate the rotor equal to the 90 electrical degrees, as you can see here, so the flux in front of this coil is equal 0, because This flux, the half of the coil span is in front of North Pole and the other half is in front of the South Pole. So the net flux linkage is 0. As you can see here, lambda is equal minus n phi gap divided by 2 plus n phi gap divided by 2 at this point. Okay, this is flux linkage. This waveform is flux linkage versus electrical angle, and this is when the electrical angle is equal pi divided by 2, the flux linkage is 0. And if we rotate the rotor 90 degrees more, so the coil will be in front of the North Pole and the flux linkage will be equal n times phi gap, right? It's very simple. So in ideal case, if we neglect magnetic saturation, we have this waveform, triangular waveform, and as you know, the induced back EMF is derivative of this waveform. Okay, in this case, the derivative of flux linkage d lambda dt is positive. We have positive slope, and derivative here is negative. Okay, this is ideal case, but in real case, as you know, because of saturation or properties, nonlinear magnetic properties, we have something like this. Okay, we don't have sharp edges. Okay, so this was for one coil, but when we have distributed coils and winding, we can use similar concept. The phase back EMF is equal d lambda dt, derivative of flux linkage, and if I expand this derivative, I can change this variable time and rewrite it in terms of electrical degrees. So I can write d lambda d theta e divided by d theta e dt. This is electrical angular speed omega e, and d lambda d theta e, I can calculate it in actually in half electrical period. Okay, and as you know, omega e is equal omega m times nm divided by 2, right? We have this equation. Electric speed is equal mechanical speed times the number of pole pairs. So what is the value of d lambda d theta e? We have this variable lambda max, that is the maximum flux linkage. Maximum flux linkage is equal pole flux times number of effective turns per each phase times winding factor. So as you know, if I show you this figure, we have a number of poles on rotor, and in average we have a specific amount of flux under each pole. This figure shows the radial component of the flux density in the middle of air gap versus rotor position or distance. The number of poles here is high. So we have a specific amount of flux under each pole. So what is the maximum possible flux linkage for each phase is equal number of effective turns per phase, this equation, times pole flux. But because we use distributed winding, we cannot capture this amount of flux. And what we get in winding is lower. So we define winding factor. Okay, so the maximum flux linkage is winding factor times NT phase times Vp. So induced back EMF E phase is equal. If I see this figure, I can calculate induced back EMF. What is the variation of the flux linkage in half of the electric period is from negative NF gap to NF gap, or actually 2 times lambda max divided by pi electric degrees, right? So this is the phase back EMF. But we should correct the phase back EMF equation, because as I said, this is for ideal case when we don't have magnetic saturation. But in real case, we have saturation and we don't have sharp edge. So this figure shows phase flux linkage for a 3-phase BLDC motor. And if I want to calculate the phase back EMF, I should calculate the derivative of this waveform. As you can see here, the derivative in the middle of this waveform here is max. So the maximum phase induced phase voltage is higher than this expression. If I calculate, you can see the line 2, the red line, okay, the slope of red line and the slope of this blue line. So I define a slope factor that is a slope of line 1 divided by the slope of line 2. The slope factor is higher than 1, and the maximum phase flux linkage is a slope factor times this expression. Okay, so I can calculate the maximum phase flux linkage. I have these variables here, winding factor and slope factor. Winding factor and slope factor is a function of number of stator teeth, number of stator slots, and number of magnets or number of poles. Because at the beginning of design we don't have any idea about these numbers, and we need them to start the design, we have to assume proper numbers. Okay, so in this step I suppose proper numbers for winding factor and slope factor. Then I design the motor, and I calculate, after finite element calculations, I calculate a slope winding factor and a slope factor and update them here and do it iteratively to update the design. Remember this iterative procedure. Okay, so we assume proper numbers for a slope factor and winding factor. We do design, do finite element calculations, and update the design again and again to satisfy and to match the numbers. Okay, so this is the equation for calculation of the slope factor. In finite element software, we will use this equation to calculate the slope factor. Okay, so its explanation is easy, and you can investigate this equation as a practice. Okay, so this maximum back EMF gives us a good idea similar to DC motor. In a DC motor, brushed DC motor, we have a back EMF E and we have armature inductance, armature resistance, and we have terminal voltage. So if I want to be in motor mode and motor operation, I should inject the current into the armature, terminal current. And terminal voltage should be higher than the motorbike EMF. And as you know, the terminal current is equal Vt minus E divided by armature resistance. So in BLDC motor, we have inverter here, and we have source, and we have motor here, three-phase winding and motor here. What is the back EMF that we get here? Is its waveform is like this. Also, we will calculate this by finite element method, right? So I have a DC voltage here, and I have a voltage like this. So if I plot the DC voltage, and if I plot this graph in one graph, if I plot these two waveforms in one graph, I have something like this. So the back EMF of BLDC motor should be such that I be able to inject the current into the motor to generate the torque, right? So this is DC voltage, this is back EMF. We calculated the maximum back EMF, and we need to set this difference and set the phase resistance, okay, to match, justify, to get this terminal current or this phase current, okay. So because of this, I defined the slope factor here and modified this phase equation, back EMF, phase back EMF equation. Okay, I think it's good for this video, and let's pause and continue in the next video. In the next video, we will continue to derive the output equation and magnetic loading concept, electric loading concept, and calculation of the motor main dimensions. So as a practice, you can review the phase back EMF equation and the concept behind the definition of the slope factor. Okay, thanks for watching, and let's continue in the next video.